Assalamualaikum everyone. My groupmates and I will present about this topic, nuclear physics. What is the electromagnetic spectrum? The various types of radiation around us are indicated in the electromagnetic spectrum below, ranging from radio wave, which is low energy, to gamma radiation, which is high energy. Radio wave have the longest wavelengths and lowest frequency in the spectrum. It's used to broadcast radio and television. Microwave, which produce more energy due to shorter wavelength and higher frequency. It's used in microwave oven, radar, telephone, and other signals. Next comes infrared light. The sun, fire, living creature, and other heat resource all produce infrared light. While we cannot see infrared light, we feel it as heat. Visible light occupies a narrow slice of the electromagnetic spectrum nestled between infrared and ultraviolet. Visible light also makes things able to be seen with our eyes. Red color wavelengths have the lowest frequency and longest wavelengths of visible light. As you move from red through orange, yellow, green, blue, and finally purple, wavelengths shorten and frequency increase. We move into ultraviolet frequency. Human skin produces vitamin D when exposed to ultraviolet light, but excessive ultraviolet light causes sunburn. Next is X-rays. It's used to view inside of bodies and objects, usually for medical tests. X-rays also have security applications, such as airport baggage check. Lastly, gamma rays produce even shorter wavelength and highest frequency. In general, the radiation is divided into two types. First, ionizing radiation, and second is non-ionizing radiation. The wavelength shorter than 100 nanometers is classified as ionizing radiation, for example X-rays and gamma rays. Wavelength longer than 100 nanometer is classified as non-ionizing radiation, for example radio wave, microwaves, infrared, visible lights, and ultraviolet.
Hello everyone, I'm Aminuddin. How are you? You'll be fine, I hope so. In this video, we're gonna take a closer look at the type of nuclear radiation, namely alpha particles, beta particles, and gamma rays. We'll also cover how ionizing and how penetrating each of them are.
Let's start with alpha radiation.
Alpha particles are made up of 2 protons and 2 neutrons, which is exactly the same as the nucleus of a helium atom. So we normally represent alpha particle with helium nucleus symbol He. Alpha particles don't have any electrons, so they have an overcharge of 2+ from those 2 positive protons. Because they are relatively large, alpha particles are easily stopped by collision with other molecules, which means that they can't penetrate very far into other materials. In fact, they can only travel a few centimeters in here and absorbed by a single sheet of paper. However, their large size and a strong charge does make them very strongly ionizing, which means they can easily knock electrons off any atoms that they collide with. Next up, we have beta particles, which are just electrons, so they have a charge of -1 and virtually no mass. Now, the weird thing is that electrons aren't emitted from one of the atom shells. Instead, one of the atom neutrons decays into a proton and an electron. The proton stays in the nucleus, but the electron is emitted out at high speed. Because beta particles are pretty tiny, they are moderately ionizing, and they penetrate moderately far into material. For example, it would take several meters of air or about 5 millimeters of aluminum to stop them. Now, gamma rays aren't particles at all. They are actually waves of electromagnetic radiation, and they're often emitted after alpha or beta radiation as a way of the nucleus getting rid of a bit of extra energy. And they don't have any mass or charge. They tend to pass straight through materials rather than colliding with any of the atoms, which makes them only weakly ionizing. This means they can penetrate really far into materials before being stopped. So it can travel long distances to air, and it takes thick sheet of lead or more 4 meters of concrete to stop them. That's all for me. Thank you for listening. Hope you guys have a bright day ahead.
Hi, I'm Muhammad Admin bin Bazli. So next I will talk about the radiation detectors. Radiation detectors is an appropriate instrument that are necessary to detect and measure the ionizing radiation that cannot be detected by human sense. All methods of detection of ionizing radiation are based on the ability of such radiation to cause ionization directly or indirectly. These instruments are created because to follow the law of radiation protection regulation in 2000, where the radiation source must be returned to its safe position or to check that contamination of surface has not occurred. Next, there are 4 types of radiation detectors, which is portable radiation monitors, area radiation monitors, personal dosimeter, and monitor for internal radiation contamination. Firstly, portable radiation monitors. Portable radiation monitors is a battery-operated handheld meter instrument. It commonly used at the radiation facilities and work site to ensure that the radiation level is within the limit specified. It usually consists of a probe or detecting head and the associated electronic circuitry. For the probe and detecting head, I will explain more details in the next slide. Sometimes it fitted with a removable shield to allow measurement in mixed radiation field. These are some examples for portable radiation monitors that might have a different probe or detecting head, such as GM tube, scintillation detectors, ionization chamber, and others. This is the schematic diagram of GM tube that operate when the ionizing radiation penetrates the mica window. Beta particles will attract to anode due to negative charge and will read by the survey meter output as the measurement. Due to low penetration level, alpha particle will attract directly at the cylinder wall or cathode. Then the measurement will show on the readout. Next, the advantages of using GM tube is it has higher sensitivity compared to ionization chamber, also relatively inexpensive, and have small size and volume that possible due to higher sensitivity and energy concentrated instrument suitable for measuring ambient dose equivalent. There also have disadvantages on GM tube where no energy discrimination is possible, also saturated at high dose rate, and that time is about 300 microseconds and cannot be used to accurately measure the pulse or source of radiation from accelerators. Lastly, most portable survey meters are intended for dose rate measurement, while some have integrated facilities which enable to the total dose in the given time to be recorded. It also must be calibrated at periodic interval in a radiation calibration facility. Radiation meters is an instrument that specializes for indication of external radiation level present in an area where ionizing radiation are present, such as in the mine. It also produces hazardous alarm if the level exceeds of predetermined value. It is designed to respond to gamma radiation and may use either GM tubes or ionization chamber in the detecting heads. These are some examples of area radiation monitors that located at specific place to detect the ionizing radiation. Next, ionization chamber have similar diagram as a GM tube, with additional plate and inert gas. When ionizing radiation go through, it will forming an ion pairs that effect potential gradient electric field within the gas. The positive ion attract to the negative plate and vice versa. The collection of ion will produce charge and electrical pulse. Measurement will pass through to the readout. There is advantages on ionization chamber, which is it can be used in pulse radiation field, can measure accurately beta radiation with window slide provided, can measure very high radiation level with little no dead time, also more reliable in case of high dose rate. The disadvantages is detector operate in current mode with air as field gas, has flat energy response above 100 kilo electron volt, no gas application is required for operation, designed to measure only X-ray and gamma rays. Lastly, due to the technology development, gamma camera has been created with a visual output to detect the radiation. This is an example of gamma camera employed at Fukushima, Japan.
Hi, now I'm going to continue from this part, which is personal dosimeter. Overall, a main component of radiation dosimetry is personal dosimeter. Personal dosimeter is mainly used to assess doses for people who are exposed to radiation due to their activities at work. Usually, these doses are measured by instruments referred to as personal dosimeters. There are three types of personal dosimeters, such as thermoluminescent dosimeter batch, quartz fiber electroscope, and beeper. Let's go through this instrument one by one, shall we? The first one, thermoluminescent dosimeter batch. Thermoluminescent dosimetry is a phenomenon used to detect and quantify exposures ionizing radiation using solid-state detectors. When exposed to such radiation, free electrons are trapped in lattice imperfections in the TLD crystal. The electron escape the traps and release light when heated, typically to 300 degrees Celsius, which can then be measured using photomultiplier. An observed quantity of light is related to radiation received. In the parts of the TLD batch, the TLD structure is plastic holder, nickel-coated aluminium card with TLD disc, which the disc is made from calcium sulfate doped with lithium fluoride. It has 3 against each disc, which on the top is aluminium and copper, while in the middle is perspex, and the lower is open. Here are some precautions and ways using the handling TLD badge. The user must wear the badge at chest and waist level, and if a lead apron is used in an X-ray area under the apron, the user must also not share the badges and do not move the card within badges. The second one, quartz fiber electroscope dosimeter. A quartz fiber dosimeter, or sometimes called a self-indicating pocket dosimeter, is a pen-like device that measures the cumulative dose of ionizing radiation received by the device, usually over one work period. The structure of QFE consists of an ionization chamber with a volume of approximately 2 ml, which is sensitive to a desired radiation, a quartz fiber electrometer to measure the charge, and a microscope to read the fiber's image of a scale. Here are the image of QFE. Advantages of using this device are it is immediate reading and energy independent of wide range of gamma rays. The disadvantage of QFE is its low accuracy and susceptible to moisture. Last one is beeper. The beeper tree is a simple, convenient instrument for alerting personnel to the presence of X-ray or gamma radiation. The instrument operates continuously and provides a clear, audible indication of those rates. While it produces a blip every 15 minutes for a normal background radiation, the frequency of the blips increases with dose rate until a continuous tone is achieved in high radiation fields. This part is on how to monitor for internal radiation contamination. There are a lot actually, but I'm going to go through only one way, which is personal monitoring. It is divided by two, which is external exposure and internal exposure. For internal exposure, it has two methods, which is biopsy method and whole body counter. Internal exposure monitoring is required to personnel who work with irradiating apparatus and all types of radioactive sources. Radiation workers are required to wear a device known as personal dosimeter, which is used to measure the radiation dose received while working within radiation area. As for the internal exposure monitoring, the whole body counter is a direct method where its radiation dose is measured using measuring instrument, while the bioassay method is an indirect method which requires sample, namely urine, feces or sweat.
Let's proceed to the next subtopic, which is radiation safety. Dose limit. It is recommended by ICRP as specified in radiation protection. It is divided by two. Dose limit for radiation workers. It is designed to prevent the incidence of deterministic effect by keeping the dose limit below threshold value. Second is to ensure that protection is optimized and exposure are all kept as low as reasonably achievable. Third is 20 mV a year recommended by ICRP and does not exceed 50 mV in any single year. Dose limit for public. For member of public, the dose limit is 1 mV per year. Alara principle is applied. The dose for women who are not pregnant shall be same as men. Once pregnancy has been declared, those limits shall be 2 mV for the remainder pregnancy. Source of radiation are divided by 2. First is natural source. This contains cosmic radiation, terrestrial radiation, and internal radiation. For the second one is man-made source. That is any radiation source produced by humans, for example, X-ray. There are 3 principles of radiation safety. Time. Radiation exposure can be accumulated over the time of exposure. Second is shielding. There are many shielding devices such as caps, glasses, gloves, and others. Lastly is distance. A greater distance from radiation source can reduce radiation exposure.
Radiation accident is a radiation accident. A radiation accident is defined by the International Atomic Energy Agency as an event that has led to significant consequence to people, the environment, or the society. A radiation accident is an unintended event occurring with a radiation source or during a practice involving ionizing radiation which may result in significant human exposure or material damage. Next we go to the how does this radiation accident occur. The accident occurs when radioactive material comes into contact with person's hair, skin or clothes, people swallow or breathe radioactive material, and radioactive material released into the environment. Next, we go to the history of the largest radiation accident ever happened in the world. This is the location of the country and the date when the accident happened. Next, we go to the emergency procedure. Basic protection action: less time spent near source, greater distance from the source, behind shielding from the source. 4 major steps for emergency procedure. First is decontamination, second is personal protective equipment, and third is dose monitoring, and followed by medical surveillance. Decontamination of emergency response worker, their clothing or any equipment including PPE they may be using is essential to limit radiation dose and prevent the spread of radioactive contamination outside of the response area. Employees whose worker may be contaminated should establish procedure for radiological monitor and surveying workers to identify which, if any, are contaminated and to what extent. Protective equipment (PPE). PPE is equipment worn to minimize exposure to hazard that other workplace cannot control, including engineering control, administrative control, and safe work practice cannot control. During a radiation emergency, PPE will not protect workers against most types of direct external radiation exposure. However, correctly using proper PPE will help prevent or minimize any internal exposure by preventing ingestion, inhalation, or skin absorption of radioactive material. Dose monitoring. Dose monitoring is a device that detects a radiation dose rate, or it may help employer or workers identify the boundaries of area with radiation level of concern. In area where there is radiation, response workers should be equipped with appropriate radiation monitoring equipment. If possible, use equipment that provide unambiguous alarm based on predefined levels. Medical surveillance. Workers who are or may be exposed to hazardous substance or health hazard at or above the established permissible exposure limit, above the published exposure level for this substance, require that employers make medical exam available to covered workers at reasonable time and place prior to employment, periodically once every 12 months. Face, symptom, and etc. There are several phases and symptoms for those who have been exposed to radiation.